Well, hi everybody. Okay, thanks a lot. Hi everybody. My name is Gabriel Kastenbaum, and I'm here to talk to you about Erlang. And I'm a developer. I work in Erlang for 4 years now, and I've learned a lot during that 4 years, because the more I use Erlang, the more I learn about how you do things well, how you scale well, and how you can create some great applications. And that's what I want to talk to you about today. That's experience about how to do things in a way that is not well known, in fact. So, back in the time, when Erlang, well, what I like in Erlang is that it comes from the trenches. It comes from the past, from the telecom world in the late 80s and the beginning of the 90s, where people had a problem which was scalability. They wanted to connect millions and millions of devices on phones and have a new switch that could handle all that communication. And they tried to do it in C++. Well, that didn't work at all. And some guys in Ericsson said, well, maybe we can try our new language, which is Erlang. And that's what they said. That's what they did. And so they, in that way, they managed to program something that was not able to do, that they didn't do in C++. And so, I mean, Erlang was done with really good constraints and really great requirements from the beginning. The software had to be always online. There is no downtime. The switch in telephony cannot stop, otherwise it will be in the newspaper the next morning. Of course it's distributed because there are thousands and millions of connections, and it's real time, and you have to upgrade your software without to stop the system. You never stop the system. It means that if you have a bug, you just upgrade the machine. But how do you do that? That's quite a huge problem. So that's what Erlang had in mind 20 years ago. And if you think about it, all these problems are, in fact, exactly the same problem that we have today with our internet. Look at the Reactive Manifesto. It talks about responsiveness, about how to be resilient, and how application must be with message passing, etc. All this was in the requirements of the telecom companies in the 90s. That was a problem that already exists. So it means that maybe we have something to learn from that time, and maybe they did it well. And I think, in fact, they did. And in the second example, to see how much that requirements are today's requirements, if you see in Spark the central concept, it's called RDD. The two first words here are resilient and distributed, which are two main characteristics of the Erlang platform and the Erlang applications. I mean, parallelism is a problem that we have today. Scalability is a problem that we have today. As you can see, scalability is hard. That's a picture that I took yesterday when during the party, when everybody wanted to have features. And you see, it's hard to scale when there is a lot of people going there. So, how do you do that in Erlang? Yes, you're right. Maybe I'm going to shave. That's better. Is it better? Yes, you're right. You're right. It was scratching. Thank you. So, here let's go with the principles. And how do you do something that really, how did they manage to do something that succeed in that real hard problems? First, they had 4 points, and my point of view. It's a simple language. They use a lot of functional programming. They use concurrent programming with processes. They can create a lot of processes. And there is isolation, as we'll see. It's a simple language. Here, it's only 1 page, and here are all the commands of the language. You can find it on the internet really easily. It's a platform, which means that you run things on a virtual machine. For instance, let's start a virtual machine in Erlang. It's called REL in a Linux. And there we go. We have an Erlang platform. And we can do an add, which is really useful. You can go shopping with an Erlang machine. That's great. You have a repo, and in order to solve the problems of scalability, let's be functional. The guys that created Erlang just choose to be functional not because of theory, but because it was the solution. First, let's use functions. Why use functions? Because a function is something that you give it some data in, it processes it, and you have data out. There is no state. It means that if you want, for instance, to upgrade that function that doesn't work, you just remove it from the virtual machine and you put another one on place. That's how the code reload will work. I will show you that. That's pretty magical, in fact, and I'm happy to be able to show that. That's why functions are the main thing that works. Second thing in functional programming, it's immutability. I'm sure you've heard that hundreds of times now during those days, but immutability means that you can go parallel, you can have a parallelism, and you can go with associativity, you can scale. When you have immutability, you're sure that one process has the data, another process will not change the data. It means that you're sure it's a relief when you're a developer. You don't have a problem of saying, well, maybe someone will change the data. No, that won't happen ever. So that's about immutability. So now that we can scale, what do we scale? We scale processes. They are very lightweight. I'm going to show you that in a demo. You can create hundreds and thousands of them. They will communicate via message passing, and the message are written by copy. You could just create a message. Here are all the things to do some message passing in Erlang. That's a lot, 3 things. You create a message with a spawn. A message can receive a process can receive a message, and that's receive. And you can, as a process, send some message to another process with the bang. That's more or less exactly the same as in Akka. And by the way, all the processes are actors, which means that they have a list of, it's a box where they will receive all the messages and they will treat it all the way along. And that's why all is isolated. Okay. That's the most important thing to understand how Erlang works, how to do something that will scale well. It's isolation. I mean, there's no shared memory between the process. All the processes are all different. All the processes have one garbage collector, and which means that if the garbage collector begins to work, it won't stop the whole machine. It will stop only the one process. There is no stop the world effect. Okay? And that's the difference with my Elasticsearch server, for instance. And isolation means that if a process falls, the other one will continue to run. And it also means that you can create an architecture where there is a process that will only spawn one other process and will look at the process to see if it works. And if that process which is here fails, you will restart it. That's the basis of OTP, etc. That's why it can scale, and that's why it deals with fail detection, and that's why it works. Okay? So let me show you, for instance, a little bit of code, of a little demo. Okay, that's not too big. With a tennis table player. What is a tennis table player? That's someone who is here, it's a process in fact, will receive messages, right, left, and will do some forehand or some backhand. That's really simple, but in real life, that's a good analogy. It's not as a funny, comment tu dis, funiculaire, but that's good too. So here is our player. I'm going to show you that when you have in my player, I just started my player and I will send him on the right some forehand, on the left some backhand. And you say, oops, because he doesn't know how to do that. So what I can do, I will patch the code and I will not stop my application. I'm live. And let's patch my code, because my code doesn't work. When there's a ball on the left, it doesn't work. So I just wrote the code. I just have now to compile. C means on the report, let's compile and reload the code. You can reload the code and then, well, you see, I didn't stop my machine. The system is always on, and I upgraded it, okay? That's quite simple, in fact. And that's what I do all day long. I patch my system, and it never stops. But how is it relevant? Is it okay to create a lot of processes? Will it scale? Well, let's do another demo where I don't have one, but I have many players. And let's say, for instance, 10,000 players, and throw them 5 balls. They will have 5 balls, and they will play. So 5 times, it means that they will have 2 times 5 times 10,000 messages. I mean 100,000 messages. Okay, let's do that. There was 10,000 processes and 100,000 messages in 1/3 of a second on that laptop of 2 years ago. It means that it's pretty fast. You can try it with threads if you want. Let's try to add some balls. And here I had a 0. It means that there is 1 million of messages, and it's in more or less 2 seconds. Okay. So now let's try to do it with, you see here, 100,000 processes. Why not? And it will take more or less the same time. And I created on that simple laptop 100,000 processes. It means that it's very light, very fast, and you can use it without an headache. That's the main idea. To summarize, first, what I like in Erlang is that it's done right from the beginning, from the foundation. And second thing, that if you want to scale, one of the possibilities, there are others, but the best possibilities to me is to have the possibility to have many processes that you can spawn, and immutability and functional programming is mandatory. And third, that all this is inside the language. I mean that when you want to have more possibilities, more features, just look inside the language, learn the languages, because you will learn a lot of things about how to do things right. Sometimes the things are inside the language, and it's the right level of abstraction. Voilà. Any question?
Yeah, so when you reload,
yes.
how do you reason about the state of the program? I mean, there's some state.
There is no state.
Well, I mean,
that.
Yeah, I mean, it's not, I mean, it's you started
yes.
some process, and so during that, while it's running, it knows that it's running this thing.
Yes, absolutely.
But it's really just a symbolic expression that is.
It knows that it's running, but the function has no state. It has no value that is hidden somewhere or something like that. As it's a function, and you only replace the function, so the invalid function is replaced by the virtual machine, and you put a new one in place, and you continue to run. If you want to have state in Erlang, you just do functions that would call the functions again. That's how you deal with state. And you stop here with a receive and you wait something. That's all OTP is about.
So suppose I have a recursive function and
yes.
you load, at some point the old version calls the new version.
Yes.
That would be a way of thinking about it. Okay.
Yes, yes.
So then you have to think about backwards compatibility, I guess.
About?
Backwards compatibility.
Absolutely. Absolutely. That's one of the points. If you have big patches, when you upgrade a lot of things in your code, sometimes the patch is bigger than the code itself. You have to say, well, I have some structure here, and I have to move, to change, to add something here, etc. That's true, but in fact, one of the characteristics in Erlang is that it's dynamic, there's no object, and there's no such things, not many things as structures data. So if you don't have so much that problem because it's dynamic. If I send you a client with 5 fields, and then I send you a client with 10 fields, it doesn't matter to me because it's just dynamically typed. You see what I mean? So you're absolutely right anyway.
And so how do you test that then?
You test a lot. That's very important. That's very important. I have, yes, that's why it works. It's because you have tests that will validate the thing that your function will take something and respond something else. But as it's functional, you're sure that there is no state somewhere, some other effect that will change your function. That's why it's easier to state too, because it's functional programming. See, but it's true that you don't have the validity of a static language, just like Haskell or others. And you don't have the problem in Scala, for instance, which is great for them, but they have other problems, just like Paul Phillips is talking about. Thanks a lot.